We're going to present here fractions with more complex denominators, starting with this one right here. And what we need is to eliminate square roots from this denominator. I'm going to create a quantity cube, which is going to be the same as that denominator. But with a plus sign. So that would be 7 square root of 2 plus 2 times 3 to the 1/2. My new numerator is going to be the previous numerator multiplied by that quantity q gives me this result. And the denominator, the new denominator will be the old denominator multiplied by the quantity q. And so with that, if I put together my fraction as the new numerator divided by the new denominator, I get this result. There are square roots in the numerator, but the denominator is totally simplified. Using radcan for simplifying radicals, I was able to reduce my result to this value. Example 2. I'm going to create a quantity cube is going to be equal to 6 plus the square root of 6, and I'm going to expand my denominator, my numerator multiplied by that quantity, and the denominator is going to be d multiplied by that quantity gives me the q. So my new fraction is going to be n over d, which is this result right here. I'm going to try radcan of the previous result, and that simplifies to 16 square root of 3, 3 plus square root of 2 over 10. And so we simplify, we are rationalizing the denominator in these cases. The last case is this one. Now this is going to be a little bit more complicated. I'm going to create a quantity that is going to be, let's say q1, and it's going to be equal to the square root of 3. Sorry, let's put it right here, plus the square root of 2 plus the square root of 5. That's going to be like multiplying this quantity and then changing the sign of this minus 1 right here. And so my new numerator is going to be multiplied by this q1, and my new denominator multiplied by q1 gives me 3/2 the square root of 3. That's still, if I do n over d, it's not rationalized, but the denominator became a single quantity. And so all what I have to do now is the current n and d values, I just need to replace them by, I just need to multiply by the square root of 3. Well, no, actually there's a square root of 2 here, so I'm just going to multiply by this full denominator. So I'm going to expand, and I multiply by the current denominator, and then the new denominator will be expand d times d. That gives me 24. So my new fraction is going to be n over d, and I'm going to do a radcan, and that is my result. So that ends up this presentation about radicals, about rationalizing radicals with complex denominators. With radicals, they're reduced to first order. There are a few of them. What I'm going to do here is subtract the square root of x plus 1 and raise both terms to the square. Expand that. Subtract the left-hand side. Add the radical term in there. Then divide by 10. Square that term again. And so you end up with an equation that's easy to solve. Actually, you don't need to solve here. x is equal to 5. This happens to simplify to first order equation. Or if you have that, you can use solve. But solve doesn't work here. And it doesn't work. It just doesn't want to do it. So we could try to find a numerical result with find root. Here's another example. And since I have 4x minus 3, I'm going to call that term t1. So I'm going to multiply the left-hand side by t1 and the right-hand side by t1, expand that result. Add 4x plus 3 to keep the radicals in the left-hand side. Divide by 2. Raise this to the square. Expand that result. Move everything to one side, and then we end up with a linear equation whose solution is x is equal to 3. So radicals in Maxima are not as straightforward as in the textbooks, but you can always use float to obtain a numerical result, and use rat simplification or ratcan to try to simplify radicals. And with that, we finish this particular video.